Today I have a busy schedule. Um, Half of the first half of the lecture of the today will be uh, will be exploring the kind of consequences of the physics that we started to discuss last time, the thermodynamics. So we are moving from the micro dynamics, micro picture of the world to macroscopic description. And we'll start with equilibrium, then we'll talk about approach to equilibrium, then about non-equilibrium systems in general. And then the second part will be um, going to brain dynamics. How do we model the dynamics of the relevant degrees of freedom in the brain in relation to computation? And we'll discuss, we'll maybe critique what is this a good model framework or some what is missing there and so on and so forth. Okay, very good. So let me just begin by a recap of what we had last time. So the thermodynamic picture that I portrayed last time is basically what's known as Boltzmann theory or Boltzmann picture. And let me just remind you that it approaches thermodynamics from the perspective or the simplest perspective of large closed isolated system. We have a phase space for that system. Every point in that phase space is a microstate of the system. There is a hypersurface, a sub-manifold in that big hyperspace phase space, which correspond to all microstates in a fixed energy. And since we are talking about closed isolated system, energy is conserved. So everything happens in this slice, but this slice is still subdivided into macroscopic states, or a microstate with a given set of values for the macroscopic variables. So that's what's called macrostate. So this is gamma m. So the gamma E is now tiled into all possible macrostates. However, the overwhelmingly large, the largest volume, but by far, of among all the macrostates is the equilibrium macrostate. The equilibrium macrostate basically occupies most of the microstates in phase space when the system is large. And therefore, most of the, before that, and then when we talk about approach to equilibrium, we talk about dynamics, and the dynamics is very simple. It follows the microstate dynamics, Newtonian mechanics. It follows that. So gamma of t, so the macrostate dynamics is simply whatever the microstate evolution in time evolves. So we have these trajectories crossing one macrostate to another. And then the final punchline is that because almost all microstates are in the equilibrium state, then it follows that almost all non-equilibrium microstate initial conditions will be in the equilibrium macro domain. That's basically the picture. And then there is entropy because we're going from small volume to largest volume. Then entropy is defined as the log of the volumes. It increases with time. And we discussed the past hypotheses and whatever interpretation we have for that. So that's the picture of the Boltzmann picture is clear, is clean. We don't have to invoke other parts of the world aside from whatever this closed isolated system is. And also, we don't really talk about probabilities. We just say we compare volumes. And then we have argument that if this is so big a volume, most of the trajectories will go into them. Okay. despite, despite the fact, or maybe because it is so simple and clean, it is useless. In most calculations of macro properties, we don't use Boltzmann theory. Uh, Rather, instead of that, we use Gibbs theory. And Gibbs and Boltzmann were two giants, which founders of statistical mechanics, but they didn't agree about how to approach it. So let me talk about Gibbs' approach. And Gibbs' approach is mostly well-founded, well-defined when we talk about equilibrium. So now we are back into the notion of equilibrium state, but in Gibbs, equilibrium is defined by a probability distribution of all microstates. So again, X is one of the microstates in the entire phase space. So we're not conserving energy anymore. We are talking about closed system, not isolated. And the equilibrium macro state is specified by an equilibrium distribution over all possible microstates. So that's P or P for Gibbs. The Gibbs distribution over all microstates is given by the famous exponential minus the energy function of X of the microstate multiplied by beta, which is the inverse temperature. One over beta is Boltzmann factor, you know it, and temperature. So it's very simple. If the temperature is very big, beta is small, then basically you explore uniformly all microstates in the phase space, in the constrained volume, whatever there are constraints in the physical world. And if beta is large, temperature is small, then this distribution is peaked around the low energy state. I think most of you, probably if not all of you, know about this Gibbs distribution, e to the minus b. Sometimes it's also called Boltzmann distribution. Anyway. Then there is the normalization, 1 over z. Z is called the partition function. And the partition function is simply to normalize this distribution. It's integral over all x, e to the minus beta x. I'm writing integrals. Sometimes we'll do summations. That's fine. I'm not concerned about that. Okay, another important, the partition function from kind of as a statistician, it would just be some normalization. But for physics, it's an important quantity, and rather the log of it. So you can think about z as kind of weighted volume of the phase space, entire phase space. And therefore, it is exponentially large with n, where n is the number of degrees of freedom, or the total volume in the physical space. The log of that is an extensive quantity. It is linear in the number of degrees of freedom on the volume, and that's called the free energy, F. And it consists of the average energy minus inverse entropy. And the reason I'm bringing this up, we're not going to do detailed calculation, but to give you an example of what we do with this Gibbs distribution. So one of them is defining the free energy, and now the energy is defined as an average of a Gibbs distribution of E of x, and the entropy is minus p log p average over all, integrated over all x, the famous minus p log p expression, which occurs, of course, you all know that occurs also in Shannon basic information measure. All right, so this is all this quantity is equilibrium, and this you can think about this last equation for entropy is kind of generalizing Boltzmann, because if you were in the condition of an isolated system where the energy is fixed and you only look at the and you uniformly sample in all states within a given energy, then P will be constant and will just be, the log P will just be proportional to the number of states. So this will be like Boltzmann entropy. But Gibbs is much more powerful. It is can be applied to any system you could not is isolated, any system at equilibrium. And you all know what context that the entropy also occurs in computation and information. Okay, that's the Gibbs picture. Okay, and that's the bread and butter of statistical mechanics. You write down the Hamiltonian, the energy function of the relevant degrees of freedom. You construct the Gibbs distribution, and then you either study it analytically or sample from it or whatever to derive predictions or to derive the properties of the system from this theory. All right, so the question, that's called canonical ensemble, but I don't, okay. So the question that I want to spend a few minutes on is to elaborate on the miracle of starting from a deterministic system until now, including in Boltzmann, everything was deterministic, we have trajectories converging in some place in phase space into a statistical distribution, probabilistic distribution on microstate, where this probability came from. Okay, so this is I think the important question, and there is no really agreement about it. Although everybody will use Gibbs distribution, there is no question that this is fantastic description of macroscopic systems at equilibrium. But what is actually happening here is less clear. First of all, almost everybody will agree that it's not coming from some bizarre, non-deterministic microdynamics. So almost all of us will agree that Gibbs distribution holds for macroscopic systems at equilibrium, even though the microdynamics is deterministic and reversible. Okay. So then there is a gap between deterministic. We discussed the gap between reversible and non-reversible, micro-reversible and macro non-reversible last week when we talked about Boltzmann, second law of thermodynamics. But now we have an extra paradox, micro-deterministic and macro-probabilistic, not deterministic. Okay? That's a new element that Gibbs put into the description of a macroscopic system. Not only not reversible, we'll come to that, but also non-deterministic. So now there are many explanations of what is the origin of this stochasticity of probability. Well-known hypothesis or explanation is saying, well, the Boltzmann is wrong, because when we are looking at a property, a macro property of a system, we don't really look at a given time and ask where the microstate is in the phase space and what are the macro properties of that microstate, which is the system at a given time. That's not realistic, and any measurement is a measurement over time. So we have to really average over a piece of the trajectory, complicated trajectory of the microstates. And therefore, we are talking about statistics in the sense that now we sample many microstates, not a single microstate that we happen to measure or we thought we measured. That has to do with time. And I won't go into that. There are complications about that. The idea that you can convert average over time to average over phase space, which is Gibbs distribution, is average over microstates in the phase space. It is known in dynamics as ergodicity properties, and there are conditions under which this indeed will be the case. In other words, that the trajectory of the system, the deterministic system, will kind of fill out most of the phase state to give you kind of what equilibrium probability will capture. Um, the problem is that there are some dynamical systems that can be proven to be ergodic, but this is under idealistic conditions. Moreover, most of the systems, either we don't know whether they're ergodic, or we can even prove in some cases that they are non-ergodic. So we have clear examples of toy models, of toy systems that are proven to be non-ergodic, nevertheless obey all the statistical mechanics, they behave normally in terms of their equilibrium. So ergodicity is too strong a requirement. So something weaker than that is needed. But that's one approach. Another approach is kind of from completely subjective, inferential perspective, saying, well, we don't know it's all the microstates. So we have ignorance about some aspect of the details of the microstates. There are some theories that connect it because it's a matter of lack of information, then it's related to information theory, and there are a whole school of thought that relates that to the kind of information question, how much information we have on the microstate of the system. It's shrouded in kind of conceptual muddiness, because it sounded like if I knew all the details of the microstate of a system at a given time, the system will not have the thermodynamic properties that are given by thermodynamics. And moreover, the more I will determine the microstate, the less I'll be, the further away I'll go from thermodynamics. And that's unlikely. And it's also, the question is, it's subjective. So is thermodynamics all about our lack of knowledge, but is it not in the real world? If we didn't exist to measure and to observe, then thermodynamics will not be valid because there is nobody to be ignorant about the system and so on. So it's, I think, conceptual muddiness, and I don't like it at all. Okay. There are two, I think, most relevant explanations. And one of them is number 3 here, which I think not all of you, or not all of you, but not many of the practitioners of statistical mechanics actually are aware of the fact that despite the fact that we write down a probability, most of the time, what we get out of Gibbs distribution is macroscopic properties, which basically do not really fluctuate. They are almost deterministic. Okay, so let me give an example. So what I mean by that is that the Gibbs distribution on this account is a mathematical construct and tool to compute the macroscopic properties of a system at equilibrium. And it's just a more elegant and a more applied, more useful way to derive equations of states and phase transitions and all the equilibrium properties than this Boltzmann. But it's not different. In other words, you can say these probabilities are just mathematical constant. Okay. So for instance, the energy which I introduced here, the average energy. Okay. So on one hand side, if I use Gibbs distribution, then the energy of the system as a macro property, important macro property, is given by this average. Okay. But as a matter of fact, if you look at the fluctuations in this energy, if you look at the variance of this energy, you find it's negligible compared to the mean. So essentially, we just derive energy and forget about the fluctuation. Another example here, which I'm bringing, is is the Ising model. Again, to those of you that don't know what it is, it doesn't matter, but simply a physical system with n degrees of freedom. Each one of them has binary values, plus minus 1 SI. So the phase space is simply 2 to the n discrete states. Very simple. We can define an energy function. I just took a simple case where the energy function is the spins don't interact, so it just minus some magnetic field times sum over all the spins. So that's well-defined system. You can write down the Gibbs distribution, and then what we are interested in magnetic system and a spin system. Most of the time, we're interested in magnetization as a function of the properties of the system. The magnetization is a macro variable, which is simply the sum over all spins in the system at any given time, okay? And now I can ask, what is the equilibrium average and the Gibbs distribution of that? I'm summing over all microstates, each one of them has a value of m. I give them the weight, the Gibbs weight, and I compute m average. It's very easy to see this trivial here. It's n times hyperbolic tangent of beta times h. Okay, so this is an example of an equation of state relating magnetization to external magnetic field and temperature, inverse temperature. Now you can also
I have a
yeah.
I have a question. So so obviously for these, Ising models, we define them however we want, and we say, they follow, these variables follow some distributions, and we can, look at their properties, averages, phase transitions, and so on. But when we say, when you said, for example, that this Gibbs distribution, kind of, when we say it's kind of an accurate description of the real world, and even though we have these, I guess, uncertainties about where exactly it comes from. So where does that confidence come from? Is it because, we do some calculations of, specific heat or something, and then it matches the real world, or?
Well, first of all, I'm not sure why you object to the Ising. Ising model, I didn't mean here as a toy model for some computer science optimization. I mean here as a physical system. When interactions of weak paramagnet, this is a fantastic model of that system. Of course, this is discrete, so you have to define the dynamics and so on. But this is the Gibbs distribution.
No, I don't object to studying the system. I just kind of more general. When we say like the Boltzmann distribution, I'm sorry, the Gibbs distribution.
Let me just finish this, and then we'll go back. The reason I'm doing this is because it's very easy for all of you to compute not only the average magnetization in this case, but also using Gibbs distribution, but also compute the standard deviation under Gibbs distribution of that property. And it's easy to see that the standard deviation will be square root of the number of spins. So you can see that the mean in absolute value is much larger than the standard deviation. And the only reason I'm bringing it is just to demonstrate the fact that most in thermodynamical systems at equilibrium, most of our attention is about macro properties. Macro properties are external properties, extensive properties: energy, free energy, entropy, magnetization, specific heat you mentioned, and so on and so forth. All these properties are derived from Gibbs distribution, but then we forget about, we don't look at the distribution of a magnetization given by Gibbs distribution. The distribution over these macro variables is very narrow. So most of the time we're just interested in the macro properties. That's what the only reason that I brought.
Haim, can I ask just to make sure? I'm not a physicist, so to make sure if I understood correctly.
Go ahead.
Is the claim that the distribution is theoretical or mathematical construct, but in actual fact, in the real world, the macro systems behave as if they are deterministic? So is that the way this is trying to reconcile the apparent paradox that there is? Okay.
I would say the other way around. So under what I claim is that the Gibbs distribution is a distribution, a broad distribution over the microstates. However, what we most of the time use it is marginalize over microstates and compute properties, macro variables, like the total energy, like the total magnetization, like the total correlations, and so on and so forth. These macro properties do not really fluctuate. They are, it's like central limit theorem. They are very tight. Under Gibbs distribution, they are very tightly peaked. And then we take the peak and forget about it. I'm saying it's just a mathematical way of computing the thermodynamic equations of state. Phase transition, gas, liquid, we want to compute all kinds of properties. These properties, we never have to look at the broad distribution. We look. Okay, so let me give you another example. To those of you know, the distribution of velocities under Boltzmann-Maxwell law, very famous one. There is a Gaussian distribution of the density of how many particles in a gas at any given velocity. Gaussian distribution velocity. I think I mentioned it last time. So, but the way to think about it from the perspective of the deterministic system is just if you take a microsystem and you build a histogram on the density of velocities, you will find this profile. Namely, the fluctuations around this profile will be negligible. It's again the same story that we derive properties from a statistical framework because it's very easy, it's very convenient, not necessarily because the real system is stochastic. Let me give another example. In some fields of physics, we use not even this canonical ensemble, but we use grand canonical. What does it mean? We say instead of having n degrees of freedom, like here in this case, we're letting n fluctuate. But we have some stochastic probability also on the number of particles. When do we do one? When we do the other one? Most of the time it's convenient. Even if our system, the number of particles is fixed, sometimes it's convenient to think, no, let's take it to not to be fixed because it's easy to calculate things. What I'm emphasizing is a truth, a practical truth, which not always we are aware of, but that's most of the time we do. Most of the time we use Gibbs distribution to compute quantities that don't fluctuate. Okay, so what I'm saying is the following. If you want to compute, let me go back here. If you want to compute, let's look here at the spin system. Suppose instead of the magnetization, I'm measuring the spin of atom number 10. Not the total magnetization, just the local spin. What is the orientation of the spin number 10? I equals 10. Well, now it's a different story because it's a microscopic variable, and it will not be. There is no central limit theorem. The average will be given by hyperbolic tangent, but the fluctuations will be large. You know, okay. So I'm saying is that most of the time we don't do that. Most of the time we don't look at the micro degrees of freedom with Gibbs distribution. We are looking at the macro properties, and they don't fluctuate. I don't know if I Liad,
Yeah, thank you very much.
What I'm saying is you have equation of state like PV equals NKT. You can derive it with a lot of work from this deterministic and the sum from the, from taking a microstate and so on. But it's much easier to derive it as if the system is stochastic and Gibbs distribution. But you'll get the same thing, PV equals NKT. The question is it easier to derive it from this deterministic picture, or it's much easier to say, let's imagine the system is stochastic and Gibbs distribution will give us the correct answer. So so now I'm going back to Hauser. What do I mean to correct answer? I have to prove that they give the correct answer. And I'm saying that there is machinery that shows that if you compare this Boltzmann picture where I look at the typical microstate and compare its macro property, I'll get the same answer as I'll get from Gibbs distribution. It's not an accident. One can actually prove it. And again, center limit theorem and Legendre transforms and so on. There's a well-known mathematics that basically show this. Okay, so that this is something which I just want to emphasize, because in physics, unlike in other applications of statistical mechanics, in physics, most of the time, that's what we do. We just compute macroscopic properties. Hauser, is this answering your question?
Yeah, that's what I was. That's what I had in mind.
Okay, very good. Okay, so now 4, but I don't want to limit ourselves to that. Sometimes we go beyond macroscopic properties. Let me give you an example of a random walk. We all know, right? So, in physical instantiation, you have a small particle suspended in liquid, and the particle gets all kinds of collisions with the surrounding molecules, and you get a kind of Brownian motion random. And you describe it by statistical properties, by probability, like random walk, probability, and so on. This is an example where you're actually looking at the particle itself is big compared to quantum physics, but that's something else. But from our perspective, we basically look at the motion of one particle, and the fluctuations are important. It's not that the distribution is wide. Okay. So what's nice about Gibbs formulation, that it covers the entire spectrum. And this is my last point 4, is that if you're talking about looking at the properties of microscopic degrees of freedom, small number of degrees of freedom, okay? So if you knew if you are interested in a particular microstate, then you get an answer, and different microstates will give a different answer. So now you're saying, but I'm not interested in what this particle or what this particular spin is doing at the time that I measure. I am interested in its statistical properties, in the sense that there may be some initial conditions in the microstate. There is interaction with the heat bath. It's not isolated system. And there is another coarse graining. That's another important concept. And this is, despite the fact that we write the Gibbs distribution on the microstates X, most of the time we use it on a select group of degrees of freedom. X is not the entire physics. For instance, as I said, this is a closed system, which means that we don't put into X the degrees of freedom, which is the heat bath around where the gas molecules, for instance, interact with the molecules of the wall. That's, we say, temperature, okay? So that's one kind of ghost graining. Or in the Ising case, in this example, I said it's a piece of magnet in the paramagnetic regime, but there are motions of the atoms, There are electrostatic interactions of all types, phonons, photons, whatever. We just ignore them. We ignore them, we mean we put them into this temperature and Gibbs distribution. So there are, so I want to summarize in the following way. That when we compute macro properties from the Gibbs distribution, then it really doesn't, then the probabilistic aspect may just be a mathematical construct. But when we take it more seriously by looking at the microscopic degrees of freedom or sub part of degrees of freedom, then indeed you are really have a genuine stochastic system, because you are saying you marginalize over other degrees of freedom which you don't take into account. So what I'm saying, that the practice of Gibbs distribution in statistical mechanics contains both. Most of the time in physics, macroscopic properties, but very often we also look at the microscopic degrees of freedom within a big system, or we coarse-grain. In other words, we are not asking the statistics of the real microscopic, but some coarse-grain variables. For instance, the magnetization here, the spin at location I may not refer to a single atom, but to a groups of atoms in the position I, and so on and so forth. So in that case, we really have a genuine stochastic system. We have a probabilistic system. All right. Okay. So one big difficulty with this approach is that with equilibrium, we have a well-defined procedure, well-defined probability distribution to work out whatever properties of the system we want. But the power of Boltzmann was that it gave us a non-equilibrium definition of entropy. Entropy of any microstate by the volume of its macrostate. And then an intuition why you're going from non-equilibrium to equilibrium, the entropy increases. But in Gibbs, it's not so clear. I don't want to go into this, but I just want to. It's an interesting observation, mathematical observation, that if you took the distribution P of X as a distribution of really all microscopic degrees of freedom, then you can show by your Will theorem that this distribution will have the same entropy all the time. Entropy will not change. Okay, so this is one problem in conceptual problem in Gibbs formulation of entropy. If you really thought about P of X log P of X as P of X at any given time of the microstate, the full microstate, S will be constant. So there is a lot of discussion about that. I don't want to get into it. But I just want to give you a phenomenology. Again, this is without coarse-graining, but again, coarse-graining saves it. If you are saying you are not defining rho of X or P of X as P of X of the full detailed microscopic degrees of freedom, but only a subset of them, a coarse-grain of them, like how many particles are in position, how many particles in a location with similar some magnetization, and so on and so forth, then you can find that it is changing. Okay. So one way to extend Gibbs equilibrium to approach to equilibrium is by writing down this. I'm not proving this equation on top here. I'm not proving it from the microscopic dynamics, but there are proofs of this it's called master equation. So this master equation is a deterministic equation, but on the probability, how the probability evolves in time. And it has the form that is given here. It's basically a linear, it's a continuous version of a Monte Carlo chain, right? Monte Carlo is basically a difference equation, discrete in time, how probabilities evolve. This is the same, but just in kind of continuous time and maybe also continuous degrees of freedom. W is a matrix, it's kind of a transition matrix. Given that the system is in X prime, what is the probability that makes transition to X? This is what's known as master equation. And what's nice about it is that you can start from some initial distribution over of these degrees of freedom and watch it evolve in time. And one can show that under general conditions, there are general conditions under which this will go into a unique distribution, and under some condition, this will also go into the Gibbs distribution. This condition are known as detailed balance. I won't go into this. I want to use this opportunity to just mention a deviation, a relation to the second law of thermodynamics. Because once we have this either Markov property, Markov dynamics, or master equations, and so on, to describe the approach to equilibrium, you can ask, okay, do we get back the second law of thermodynamics? In other words, that the entropy will evolve to maximize the entropy. Well, the answer is yes and no. Yes, if the system would be in fixed energy, but here we're talking about Gibbs distribution where we fix the temperature, not the energy. And you can show, I don't want to go into this, that you can define a free energy and a notion of non-equilibrium free energy. So what we have now is at any given time, we have a probability on the microstates, and this probability evolves in time. So to this probability, we can attach a free energy, which will be its energy given this distribution, average energy, minus the entropy, P log P, under this distribution. So now we can define a non-equilibrium free energy, which is a functional of the distribution, of the probability distribution at any given time. And one can show that if some certain conditions are obeyed, the free energy goes down, is minimized. And the free energy is minus the entropy. So this is the analog of maximizing entropy. But now it's not only entropy, but there is also energy. So beta E minus S. But it's not surprising because we're not talking about isolated system. If you consider this master equation in isolated system, you will get back E will be fixed because in isolated system, the energy will be fixed. And then free energy will be like minus entropy. But in the system, closed system, when the energy will evolve in time also, not only other properties, but energy itself will evolve in time. In that case, what you maximize is minus the free energy, or you minimize the free energy. And that's the analog, that's the generalized second law of thermodynamics. So second law of thermodynamics for isolated system is entropy is maximized. And in a closed system with the contact of heat bath at a given temperature, the second law of thermodynamics is you minimize the free energy. All right, so the one phenomenological way to capture the dynamics is by writing down a deterministic first order. Now it's irreversible, of course, it's first order differential equation on a probability. But sometimes we are interested rather in the dynamics of the degrees of freedom themselves, okay, rather than the probability. So these are two frameworks which are equivalent. So here is the equivalent. This is another way of modeling or writing down the evolution in time, the dynamics of a system which is not isolated but interact with the environment, so it doesn't conserve energy anymore, is to write down dynamics of this form. So this is reminiscent of Newtonian dynamics, the top equation, but we have two additional terms. One of them is friction, which is potentially dissipating heat to the environment. And the other one is noise, which is Z of T which is Gaussian with white noise. White noise means that it is uncorrelated neither in space nor in degrees of freedom. So these are all vectors, so Zi, Gj, and also uncorrelated in time. So what's known as white noise. And you can take this dynamics and compute the probability of X at any given time by simply averaging over this noise. And then you can show that this dynamics, the probability is obeying this kind of probability, deterministic probability equation that approach to equilibrium. So there are two ways of modeling the dynamics of systems approaching to equilibrium, closed system, not isolated, either by writing down directly the deterministic irreversible dynamics of the probability, or to write down more microscopic description of the degrees of freedom, where you add in order to capture the stochastic aspect of the system, interaction with heat bath or with other degrees of freedom, etc., you add this noise term, white noise, Z of T. Okay, the force F, in order for these two descriptions to give you an equilibrium distribution, the force has to be derived from the potential or from the energy. In this case, the potential of the system. Okay, so in both this case formulation on the dynamics of the probability, or in this formulation, in both cases, there are conditions under the driving force F of X or the transition matrices to ensure that only under those conditions the equilibrium will be what we know to be thermal equilibrium. And again, you can derive from the microscopics under some conditions that indeed those properties are held if you're talking about physical system at thermal that exhibit equilibrium. And finally, I just want to add to here. I kept the inertia term, which is the acceleration term, but in fact, many systems we just the contribution of the inertia numerically small, and in that case we're talking about overdamped dynamics, and we just have first order dynamics on the degrees of freedom. Inertia is simply negligible. And then again we have the force derived as a gradient from potential, and we have so this is the drift dissipation of energy, and this is the stochastic drive. Okay. And again here, as in other cases, and depending on the situation, remember I told you that equilibrium very often the statistical mechanics is just a construct to compute macroscopic properties which don't fluctuate. And indeed, if X is such a quantity, contains many degrees of freedom, in that case, the noise can be neglected. And in that case, you just have a deterministic dynamic like this, where F is the minus the gradient of the potential. And in that case, the system would just go to a fixed point, which is the minimum of that potential, which again, the potential in that case would be the free energy, and the minimum would be the right equilibrium. So you see that this type of dynamics with stochastic dynamics allow us to analyze both cases. Cases where these are microscopic degrees of freedom, where the fluctuations are substantial, and then you actually have to think about the system as a stochastic system and stochastic differential equations, and to analyze it in this way. Or if X is a more like macro, semi-macro variable, magnetization, energy, etc., then you just forget about the Z of T, and then you got the effective U would be, in this case, would be the effective free energy, and this will just give you the minimum of the free energy, and that's it, and that will be the equilibrium. And the trajectory to that will give you how the macroscopic properties evolve in time from some non-equilibrium value to equilibrium value, and the noise you can just ignore. So both types of dynamics, relaxational dynamics to the equilibrium value, or relaxational dynamics in the presence of stochastic noise, both have important applications depending on what is the scale, what is the type of degrees of freedom that we are trying to model. Okay. Finally, and that I'll end this part here. Finally, we can ask about systems that are non-equilibrium, that don't really approach to equilibrium at long time. Well, everything approaches to equilibrium at long time, but long time means time of the universe. And that's important because in our daily life, and definitely in biology, but not only in biology, complex materials, glasses, all of these systems have a hard time really converging to the thermal equilibrium, which we described before. And the time of convergence to that equilibrium might be so long that we're not interested in that. Furthermore, those systems may be interacting with some other systems in non-equilibrium way, not in kind of feedback way. Okay, so in that case, what we do in practice is write down the phenomenological dynamics. It will be dissipative, first order, so there is no relic of micro-reversibility. And we either have stochasticity or we have deterministic dynamics with some force f of x, which may not be derived from a gradient of potential. And then we are getting now very far away from thermodynamics and statistical mechanics, and we are getting into the world of dynamical systems. Dynamical systems, by and large, are systems for which the equilibrium properties are not necessarily relevant. The non-equilibrium systems, noise may be important, noise may not be important. In this particular example, noise is not important. And F is some function of the state of the system at a given time. So that's autonomous dynamics. F is non-linear, so it can be anything. And then, because our systems typically will be dissipative in the sense that there is no conservation of volumes, there is no conservation of energy, it's a dissipative system. Therefore, the important notion, which I didn't talk about it until now because we were dominated by reversible dynamics and area preserving, volume preserving dynamics, is the notion of attractors. When such a system evolves in time from some initial state, but in the phase space of the system, the volume shrinks as the dynamics goes along. The analog energy is dissipated. In those cases, the dynamics, the volumes will shrink to structures, to geometrical structure with low dimensionality, which capture the long-time behavior of the system. The analog of equilibrium, but now it cannot be described as some Gibbs distribution. And there are a variety of attractors. There is one of them is we discussed already in some early lecture, the kind of fixed point. You start from some initial condition and you approach the origin in this case. So this is a stable fixed point. A stable fixed point, again, is not something that you will see in reversible dynamics, the micro-reversible dynamics, but here you see. The fixed point can be also the case where you're looking at the dynamics that goes into the minimum of the effective energy or free energy, as we discussed before. In that case, the fixed point will just be that minimum of the potential of free energy. But if the system is really non-equilibrium, then the attractor may not be a fixed point. The system will not reach a stationary behavior, but will go around the limit cycle or chaotic attractors. So limit cycle shares the property of periodic orbits and dynamics because it's also periodic, but it is different in the sense that in periodic dynamics, if you change a little bit the energy, you will get another period next to it and so on and so forth. And here, this is just a limit cycle where all trajectories next to it will converge to that one limit cycle. So it's a stable limit cycle. It attracts trajectories onto it. And similarly, chaos, this chaos shares properties of chaos in the reversible systems, like the maps that we discussed a few lectures ago, but there the area is preserved. So if you start from a volume of initial conditions, the volume will remain the same, but it will turn into thin filaments that cover the phase space. Whereas here, the volume will shrink and will shrink onto a set of lower dimensionality than a phase space that you start with. And that's called the strange attractor. But nevertheless, the dependence on initial conditions and the Lyapunov exponent and so on are also valid here. So we started, let me summarize, we started with equilibrium properties. We related it to some extent, to a large extent in the Boltzmann, but to some extent in the Gibbs distribution to the microscopic dynamics of the system. But at the other end are dynamical systems that either dissipative or stochastic and dissipative, either deterministic or stochastic, which really are the way we describe the evolution in time and the statistical properties of physical and chemical and biological systems, which some of them may be approximately going to thermal equilibrium, others are far from equilibrium. Then we have to really study the entire zoo of possibilities for how such systems behave in dynamics. All right. Questions? Otherwise, we'll take 10 minutes break and turn our attention to brain dynamics after that.
Can I ask the question regarding last class? If we think about the brain, it takes non-organized sensory input and do generalization or abstractization.
I lost you.
I would think of taking sensory input and go to the abstract space. So the brain is not closed system, so it doesn't have to preserve the entropy. But where is the compensation for this?
Well, the brain, the more correct statement is the brain is not an isolated system, right? Because again, the second law of thermodynamics is about isolated system. Okay, so first of all, again, this is related to what I said about closed system. Closed system, the free energy is maximized, minimized, but the entropy can go both ways. Can be you can gain entropy by a process from the environment, or you can, in other words, you can reduce your own entropy by increasing the entropy of the environment and so on. This is for closed systems. But now, so the brain is not even closed system. But what I'm saying, even closed system, in other words, even systems that are not isolated by interacting with some thermal environment, will not necessarily decrease their entropy. Increase their entropy or preserve the entropy, because they have a way to exchange entropy with the environment. So there is absolutely no problem for the brain to generate more order than its in input, because that loss of entropy, if you want to say in this direction, will be overcompensated by whatever heat is dispersed into the environment. Okay, so if you have electrical activity in the brain, patterns of activity, you know, the system will not be, there will be other, you will generate all kinds of other products that will be eventually dispersed in the environment in a form of a high entropy matter.
Okay, thank you.
You will have to cool the system to maintain it in a given temperature. You cannot do it without you know, exchanging this type of both energy and entropy with the environment. So we see it all the time. Systems that are not isolated can and often do generate more order locally than their input. But it's only when you don't take into account the entire budget. Okay? So we started our course with really starting from some fundamental microscopic level of description of a system, the system dynamics and its mechanical properties. And we are kind of walked our way to what in practice is the dynamics that we are using to describe systems that we are encountering in our daily life, in our scale, in spatial scale, in temporal scale. And as you can see, except for extreme cases, not extreme, but unusual cases, most of the dynamics that we actually use to describe the system's properties are phenomenological, and one can say they don't. There is no energy conservation. They are dissipative, and they not necessarily deterministic, because the system is not fully described as an isolated system. So they have stochasticity in them. In physics and chemistry, very often those systems, even this phenomenological description, will convert, those systems will convert to the thermal equilibrium. Okay. But even in physics, complex materials, atmospheric dynamics, very often are far from equilibrium, so they will not go to a thermal equilibrium. Even if they go to some equilibrium, it will not be thermal equilibrium, it will not be Gibbs distribution, it will be something else. They may show even not an equilibrium in the usual sense, but they will show oscillation, they'll show chaos, and so on and so forth, like in this slide. Okay, but what's important is the dichotomy conceptually between the practice, which is very little in common to Newton's microscopic laws, but the commitment in principle to the compatibility with consistency with microscopic dynamics given by Newton's. Nobody thinks that because we write down Brownian motion as a diffusion equation, it means that there is some bizarre dynamics at the micro level, at least in the classical, as long as it's classical at quantum. Okay, so in some cases where we really are persistent and the systems are not too complicated, I mean theorists work their way to show that if you start from the Newton's dynamics, you can get to this, I don't know, master equations or something. But in most cases, this connection in practice to make it is too hard and not feasible. But nevertheless, there is no reason to suspect that there is some ghost here. We understand the need and the origin of the phenomenological dynamics that we write, despite the scientific commitment to the basic microscopic picture given by Newton and Maxwell, electromagnetism, and so on and so forth. Okay. Not surprisingly, that this will also hold for the brain. And this is why I want to, in half an hour or so, just to give you an overview of brain dynamics. Now, this is ambitious, brain dynamics. It's, you know, there are so many scales that one can describe brain dynamics. So I want to go over briefly on something which I call the standard model. Physicists, particle physicists have standard model for all the elementary, non-elementary particles and their interaction. And it's standard because it basically explains all the experimental facts. And if you want to explain some phenomena that you see in some accelerator or something, you just use the standard model. It's called standard. Okay. So I want to describe some analog, the standard model for brain dynamics. It's kind of intermediate in its complexity and phenomenological in its, and the dynamics comes, even that comes in two versions. One is stochastic. This is the top equations, and the one is the deterministic version of that. So let me go to the top equation. So you have 10 to the, I don't know, 11 billion, 10 to the 11 or 10 whatever neurons in your brain. So rather, you know, a neuron is a complex object. We are going to, in the standard model, we are going to approximate the whole neuron as a point neuron, give it an index I goes from 1 to 10 to the 10 whatever number of neurons. Or you can think about it as a local circuit. It's also fine. Most of the time, that's what we do, a local circuit. So whatever it is, I goes from 1 to n, where n is the number of neurons participating in the circuit that you are interested in, okay? And Ri of t is the instantaneous firing rate of the neuron I. So in this standard model, we don't really talk about spiking dynamics where there is a complicated wave propagation or generating of pulses. We just look at a coarser time window, we coarse grain the temporal axis, and then we count in this time window of, I don't know, 20 milliseconds or 100 milliseconds, whatever, the firing rate, the instantaneous firing rate of a neuron eye. Okay, tau 0 is some microscopic time constant which really defines our coarse graining, but let's leave it, some time constant. Single neuron microscopic time constant. Okay, so this dynamics will have on the left-hand side, typically in this standard model, two terms. The first term is, you can call it as a dissipative term, is the term that minus Ri, that left alone, if you start from an active neuron, it will, the activity, most of the time, not all neurons, but let's say most of neurons will just go to some baseline or just be quiet, okay? So that will be, they'll go to a fixed point R equal to 0. All of them will be quiet. So this is the first time. And then the second part is the driving force, the potentially activating part, which is a nonlinear function, sigma, some nonlinear function of the entire synaptic input to the neuron at a given time. Synaptic input, which either tend to increase or to decrease its rate, okay? And inside that, you have the important one is the contribution from the circle itself, from the network. So there is a summation of a Wij. Wij, the synaptic connection from neuron J to neuron I. I is the neuron that we are looking at here externally. And then that each synaptic connection connects this neuron I to a presynaptic neuron J, and the contribution from the presynaptic neuron J is Wij times Rj of t, where Rj is the instantaneous firing rate of the neuron. Then there is Hi of 0, which is the external input, which is external depending on what the scale that we are looking. If you look at the local circuit, external can be anything else coming from the brain, other parts of the brain to this circuit, or can be from sensory stimuli impinging into the periphery, sensory peripheries, and so on. So this is Hi 0. And then, again, potential stochasticity, now Zi of t. And then potential stochasticity can be partly because the external input that I talked about is more conveniently separated into some which is kind of more deterministic and repeatable, a stimulus that you turn on and you can repeat it, and the same H will come into play. And then there is part which is fluctuating wildly, and if you repeat it, you'll get some jitter, some fluctuations. So Zi of t is noise. All right. Again, depending on the situation, and particularly if Ri will not be a single neuron, but a local population of neurons, then the Zi may not be contributing something meaningful, like in the macroscopic variables that we discussed earlier. And then you write down just a deterministic dynamics, again, depending on the situation. So it is a rate dynamics because the variables, the dynamical variables are rates. So we take a neuron with many complicated different degrees of freedom because it is an extended object. And we just collapse it to 1 degree of freedom rate, and it's a first order dynamics. It's kind of a dissipative dynamics. We expect it to see attractors, but there are also external input, of course, and noise, possibly noise. possibly stochastic. So it is a special family of this kind of nonlinear dynamical systems that I mentioned earlier. And again, in the case we ignore noise and the external input will be, if it's constant, then we know that the system, no matter what, under some general conditions, will go to attractors at long time. So we can ask, attractors can be fixed points, for instance. Attractors can be periodic orbits, and we know a lot of oscillations and rhythms are in the brain, so that's nice. But there's also irregular behavior in the brain. This is chaos. So we can look for this type of behaviors, dynamical behaviors in neural systems and make the connection and predictions or confirmation of the model. Let me just give you two extreme cases. One case is where this Wij, these connections, are symmetric. So in magnitude and in sign. So the connection J, the connection that from neuron J to neuron I will be the same as the connection from neuron I to neuron J. Under these conditions and under some general other assumptions, one can show that these dynamics that will converge to fixed points, to stable fixed points. Not only stable fixed points, but also these fixed points can be described as minima of some energy function. So this is the closest that we can see the analogy with equilibrium systems. But I must say this energy here is a fictive energy. In computer science, we often, have a cost function, optimization cost function, whatever. It's not the real mechanical energy that Newton was talking about, or even Gibbs, right? This is nothing to do with the mechanical energy. It's a phenomenological energy describing, again, potential interaction between macroscopic quantities like non-equilibrium, like neurons. Okay, but that's nevertheless, the metaphor can be very powerful. And some of you know, if not, I'll just give you an example from a kind of Hopfield model of associative memory. And I can just to give you an example how you connect dynamical concepts like attractors and fixed points and energy to computation. And in this case, it's kind of modeling the retrieval of long-term memory. So in this case, here, this two-dimensional slab is a slice of phase space, the state space of the system. So this will be the activity of neuron 1, this will be the activity of neuron 2, and so on and so forth. And what I'm showing you trajectories, but rather than these micro trajectories that wander around and feel and never shrink phase space, here you see the trajectories are organizing in a way that they converge into fixed point, but not only one fixed point, multiple fixed points. And under this metaphor, these fixed points are local minimum of an energy. We can write down the energy, I won't go into that. And this local minima or global minima of the energy are really the memorized patterns. These are the patterns that are encoded into Wij in such a way that they will be actually the minimum of the energy. So these are these attractor fixed points here. And the retrieval of the fixed point, what does it mean that the brain retrieves a memory, a memorized pattern? It means that you start the system from some initial, the network starts from some initial states here, magenta or purple square here. You start from some initial state in the basin of influence of one of those fixed point memory states. And the system evolves under the dynamics and converges into the nearby memory state, which means that you kind of do pattern completion. You start from some fuzzy clues about the memory, and the dynamics of the system will converge into this state. So this is by now kind of the idea computation by attractor or by convergence to attractor. It is used in many instances of modeling brain computation. The idea is that the circuit has an underlying energy function. The minima of the energy are due to some plasticity, for instance, or some structure, underlying structure in the network, and the computation is executed by the dynamics convergent to this fixed point. This one of it. In this case, you can write down energy function. You can assume W symmetric. There are famous models of that sort. Okay. Let's look at the other extreme. The other extreme will be the same kind of dynamics, but Wij, rather than to be symmetric and to have some structure which is related to memories, completely random. So you can ask what happens if you hook up neurons with random excitatory and inhibitory connection. What will they do? Okay, and in that case, you can easily do it in simulations. You take you just sample Wij, this matrix connections independently from Gaussian distribution, and neurons. You can show that the variance had to scale with G over N. So the G is the strength, overall strength of these connections. If G is small, connections are weak. If G is large, connections are large, are strong. And you can ask what happened to the dynamics. And again, I'm assuming here the stochastic, the deterministic dynamics, and there is no external input, let's say. You just let the network run with its own dynamics. What will happen? That's the question. And the answer is that in this case, it depends on G. G will be a kind of control parameter, bifurcation parameter. So here I'm plotting as a function of time, 5 neurons, their firing rate. You can see that they just go to some baseline 0 value if G is small, G is less than 1. It's a simulation that you can yourself do. This is, in this case, 500 neurons. However, if you increase G above 1 or around 1, you can start to see interesting dynamics. For instance, here you start to see oscillation. That's what I meant. I mentioned limit cycle. So in this case, you'll start to see the system from some initial condition. Very rapidly, it will go to this oscillation. Okay. If you start from different initial conditions, they'll converge more or less to the same oscillation. So there is a limit cycle which attracts the dynamics into it. So you see nice oscillations. You can do more statistical analysis by looking at the correlation between the activity of the neurons at one time and the activity of the neurons at later time. If you don't know what it is, forget about it, ignore it. But if you do this time-delayed autocorrelations, then you find that you have, this is just one way to make sure that indeed these are nice oscillations. Everything is kind of periodic across time. I don't have time to talk about spatial complexity. Let's skip it. Now let's see, when you increase G, to 1.5, you looks more or less maybe also oscillatory, but now you can see that there is more. It's harder to make sure that these are clean oscillations because there is some modulations of the amplitude. It looks more complicated. Okay, if I want to mention, this is kind of the spectrum, how many degrees of freedom are excited. You know what principal component is, you can appreciate that, and you can see that for small g, like here, you see maybe 4 modes that are excited. So it's almost, there are 2 harmonics. If you look at the, now you see that it's still periodic, but the spatial, the period itself is more complicated, and also the number of modes are more.
Excuse me, what are the 2 axes?
So you know what principal components are?
Yeah.
What? Yes?
Yes.
Okay, so this is PC1, PC2. You take the trajectory, okay, and you do principal component. You look, principal component is basically the modes in state, the direction in state space where most of the dynamics reside. right? So you have 500 neurons, okay? I can show you neuron 1 and neuron 2, but instead it makes more sense to show you PC1, principal component 1 and principal component 2, which are vectors, directions in state space where capture the plane where most of the dynamics is, okay? So it's kind of reducing the dynamics visually to a 2-dimension to see what's really going on. Okay, so this is what you see. It's periodic, but you can see that there is structure, there is period within period, and this is the principal component eigenvalue. So you can see how many modes are excited. So it is, what I want to say is that the dynamic, you have n neurons, all the neurons are active, but because the activity is organized in kind of nice periodic structure, the number of collective, if you want, macroscopic degrees of freedom, which are really excited, is small, is few. But there's something else happens when G is, as you increase G, you can see here again, these are neurons and this is time, and you can see that there is no periodic structure anymore. Neurons are active, being quiet, active, being quiet. You have pulses of like bursts of rates of individual neurons, but there is no order. If you look at the spectrum, you can see there is some tendency to oscillate, but there is an overall decay of correlation. So after some time, 200 or 300 or 400, there is no memory from one time to that delay. And again, here in the PCA, you can see that it's noisy, it doesn't repeat itself at all, okay? And if you look at the spectrum, you can see that now there are considerable number of degrees of freedom that are excited, okay? So it just, when together with being more complex trajectory in time, it also involves activating more and more collective modes in state space, okay? So what I want to just to make sure we understand, this is a system that is completely driven by its own dynamics. There is no outside, there is no external force, there is no noise, nothing, okay? So you would imagine nothing will happen. And what is important to appreciate that in the nonlinear systems, like this system, because the sigmoids are nonlinear, in nonlinear systems, the intrinsic dynamic of a circuit, okay, can generate rich phenomena. It can rich dynamics, rich patterns in space and time emerge spontaneously, in the sense that it's dynamics which is completely generated by the dynamic rules itself. So you can go from a fixed point here, you can go from a fixed point, you can go to periodic, to more complicated periodic, to chaotic. And when I say chaos, I won't have time to show you, but you can actually show that in the chaotic regime, you have all the hallmark of chaos. If you start from slightly different initial conditions, the statistics will be the same, but the patterns will be different. In other words, the system will lose very quickly the information about the initial conditions. There is sensitivity to initial conditions. Small deviations will take you far away. So it has all the hallmarks of chaos in a dissipative system, okay? So this is important to understand. The brain is full of these circuits, okay? Highly nonlinear, and maybe not random in this extreme case, but competing in the sense that there are negative, inhibitory, and excitatory. And it's important to realize that this chaos can be doing maybe some useful computation, but can also be as intrinsic generator of noise. And when noise is important, in some computations, stochasticity is actually valuable. you can think about this as a mechanism for generating noise in a controllable fashion. It's uncontrollable because it's not simply white noise. You have a knob like the strength of the synapses that you can control the appearance of the chaos of this noise and also its spatial temporal correlations. So these are just two completely different types of dynamics and an important context in computation. One is going to a fixed point, everything becomes static, convergence to attractor, to fixed point attractor, memory, etc. And another one is kind of dynamics which continue to evolve in kind of regular or irregular fashion, and both oscillations and chaos may have important computational purposes or consequences. Okay. All right. This is not the full standard model because the brain, in order to execute computation, it has to have plasticity in order to learn new skills, to acquire new memories, etc., etc. So how do we, from dynamics perspective, how do we think about that? No problem. We just have to make sure that we remember that in reality, this Wij, which I had here, is not constant, as I assumed here, and in all these simulations. They're actually dynamical system by themselves. So you write down the dynamic equation for the Wij. Again, first order dynamics, why not? There is some nonlinear, typically it's nonlinear, there is F, there is, what will be the dynamical rule there? Well, Wij, this is the plasticity rule. This is synaptic plasticity rule. Synaptic plasticity rules, you know, there are different types of synapses, so different types of synapses may have different rules. This is why I added a subscript Ij to F. F is the rule, but F may depend whether it's excitatory, inhibitory, excitatory, etc., etc. And then this F depends on W itself, but this is the holy grail of synaptic plasticity, activity dependent. It will depend on the activity at that time of the presynaptic neuron and the postsynaptic neuron. This is Ri, Rj. Okay, so now you see that there is a dynamics which involves interaction, coupling between Wij affecting the dynamics of the rate, Ri, the activity of the neurons, but the activity of the neurons at the same time are modifying the connections. Okay, so this is why you have to take into account that as the brain is a dynamical system, the minimal model is a dynamical system having these two sets of degrees of freedom evolving in time, interacting. The synaptic connections and the activity, electrical activity of the neurons. Finally, I added another thing here, Eij, because we need some, in many learning, in many synaptic plasticity, implementing some learning rules, we need some external feedback from behavior. You know, you did something good, then the synapse should be strengthened. You did something bad, you get a reward, you get punishment, whatever. So I just put it there, Eij, some feedback signaling from the outside the circuit that guides and controls the plasticity of the Wij. All right, okay.
Haim?
Yes.
When we talk of the plasticity of the brain, so from a physiological point of view, are we talking about synapses actually being created and killed?
All right. There are changes. There are dynamical processes that will also do that. Will also make a synapse which was functional, not functional, or vice versa. Okay, but it's more complex in the following sense. If you have two neurons where the axons of one, the axon of one and the dendrite of the other one are touching or close to touching each other in proximity, then you can see how relatively small changes will make either a functional contact or unfunctional contact, either creating a contact, a synapse, or withdrawing a synapse. Okay, if the two processes, the axon and then dendrites, are very far from each other, then you need a structural growth. This is much slower and rarer, but it does happen also. After injury, for instance, or during development, of course, then you have growth process where dendrites and axon really explore distances and then finally meet each other in according to the rules. So, however, when we talk about adult brain and learning, which is not involved messing, restructuring of the brain, typically it is the changing the strength of existing contact or this type of potential synapse being actual synapse or being back potential synapse.
Okay, thank you.
Okay, good. That's an important question, but of course, the details will be complicated. Okay, so I call it the standard model because to me, at some level, it is a kind of a minimal hypothesis, which is striking in its simplicity and naivety, but on the other hand, we don't have strong reason to say this is completely silly, which is the following. Take the human brain or an animal brain, complex brain. And what I claim that under this assumption that I made, you can understand its function and kind of gross dynamics by this type of set of equations I wrote down here on top of the brain. The first one is the activity, the patterns of electrical activity, the evolution in time of those. And as we said, at the same time, maybe on a slower time scale, but nevertheless, the connections are molded and shaped partly due to the activity. So these are the synaptic connections, the plasticity, and so on. And in this picture, we can ask what is the brain, what are the constraints for these dynamics? The constraint is that there is some structural constraints. For instance, to the question that Elichai asked, some connections may not be possible to be generated. So this is Fij have some structural constraints, which tells us, what is the state space, right? And similarly, the initial condition, specifically for Wij, you can imagine that during development, the brain is starting with some Wij, so that's constrained to some degree the flexibility or how far you change the functional architecture of the brain. So this is the brain part. The brain is giving you the structural constraint, the type of neurons and the type of synapses and the type of changes that are allowed or not allowed. Okay, what about the world? The brain is not an isolated system. The world can be the body, can be the world. Okay, and in this form, in this dynamics, the world is contributing this Hi0. It can be a circuit and the world is the entire brain, or can be the entire brain. And this input Eij, which is the external input to the dynamics of the synapses, reward or punishment or whatever. Okay, so we can see in this model how the brain has this engine of rich dynamics, enormously rich dynamics on one hand side, but on the other hand side, it's controlled first by intrinsic structural constraints of the brain, what is allowed, what is not, what is the phase space of W and R, and on the other hand, by external input. Okay. That's what I would call the standard model, in the sense that 99%, I think, of our computational models of brain function you can map into this, into special choices of Fij and Wij and whatever, Eij. You can map into this. So if I take it seriously, it means if I have a supercomputer that I just have to give it Fij, what are the structural constraints on the circle? In other words, the phase space of W and initial condition, the right initial condition, and I can give it the input. I can generate a human brain in silicon in terms of function. Why not? Just first order differential equation. Okay. Now, of course, you can say it's so complicated, and I agree that it's not good enough. It's not useful. But the question is it in principle enough? I don't know. But I'm just saying here is a dynamical model of the brain. All that you have to know is how to analyze, to simulate, analyze the specific instances of this type of dynamical model. All right. Okay. There is a list. I want to clear. There is a list of all kinds of beautiful models and theories that don't assume more than that and explain long-term memory, working memory, navigations, sensory processing. I would just also say, by the way, I'm interested in the brain, but if you ask about artificial brains, artificial neural networks, they more or less conform to this. They are sometimes even simpler than that, but more or less, they have some deviations, maybe learning rules, non-local, whatever, but we can discuss it. But by and large, they are simple versions of that. Okay, so they don't go beyond, rate kind of activity, and depending on the architecture and so on, will generate different properties. But they don't assume some, that in order to explain vision, you have to have neurons with dendrites and some bizarre active channels and so on. Just rate models is good enough. So this is our current state of the art, more or less, so to speak. Okay, now is it enough? I don't know. So here's the summary of what I would call the standard model. The brain as a computing and information processing system. It's basically a dynamic of the computation or the information processing is by dynamics. The dynamics is relatively simple-minded system. It is a graph. Wij is a graph with nodes, which are the state as Ri, and Wij are the edges. However, as we discussed, the edges and the nodes on the graph as dynamics. And basically, the computation power resides in the connectivity. In other words, it's not the fact that there are zillion different types of neurons with all kinds of nice molecular and cellular properties that biologists, many of them love and devote their lifetime to studying them. So the standard approach is that's very good, that's very nice. It may have a role, it may not have a role. It's the secret is in the architecture and the functional architecture and so on. You can take a simple dynamics and one network will do something stupid and the same dynamics with a clever architecture or learning rules and so on will do what needs to be done. All right, okay. I just want to add by what is missing, and I must say this is hypothesis, but it's not. There is no theorem that it is true, and moreover, we are far away from understanding the brain. So imagine consciousness. We don't really understand brain mechanism. Liat will tell us maybe that she has made progress or her colleagues. But at some point in time, scientists assumed, or maybe they still assume, that in order to explain consciousness in complex brain, complex animals, you need to assume some specific type of neurons. Okay, could be, but this will be kind of a deviation from the standard model. That it's not just the connectivity and the collective dynamics; it's some special microscopic properties. Anyway, what is missing? A lot of missing. Okay, dendritic and axonal processes, ionica and spikes, all is missing. Fast synaptic dynamics, I don't have time to talk about it. It's structural plasticity, which already we discussed a little bit, the answer to a question. You know, not simply WIJ, but more massive structural changes, or neurons themselves change their properties. This whole slew of slow dynamics, which is missing. And here I'm saying this, to me, is probably the point, one of the major points where we are missing an important part of what is important for brain computation. All the slow dynamics, which is aside from the synaptic plasticity rule that I described, there is neuromodulation, hormonal release, protein synthesis for very long memory stabilization. All the slow dynamics beyond dynamics that I mentioned are missing. And then there are more conceptual things which are missing. For instance, the world itself, I just describe it as giving an input to the brain. So the brain has this complicated dynamics and gets input from the world. But it's not so, because the brain, through the organism, acts on the world. And then there is a whole loop. So modern computational neuroscience and cognitive neuroscience faces the challenge of describing that loop. And that's worrisome. That's frightening, because it means to understand the brain, you have to understand the world. That's frightening, right? So, you know, behavior, to understand dynamics of behavior as physical system, physical degrees of freedom, and to integrate this into a more complete view of brain function. Then there are other important aspects like development. I mentioned briefly, which is not in the standard model, because it's a massive growth and changes in the architecture and the underlying architecture, the establishment of this FIJ and architectural constraints, and even longer timescale evolution. Under some accounts, which we cannot rule it out completely, in biology, the ultimate dynamics that really explains what's going on is evolution. If you want to understand, you know, vision or sensory processing or synaptic organization, you have to really ask about comparative, how other species, how the system evolved, etc., etc. That's true for biology in general. It is kind of past hypothesis for biology or even for neuroscience. And all this list here, I'm just giving you hints about all of us, about the enormous challenge of making sense of the brain. Because ultimately, we have to make decisions about the time scales and the spatial scales that we are going to focus, but we cannot be ignorant of the broader picture, which has development and evolution and genetics, and things that it's good to make a very naive model, like WIJ, 500 neurons or 10,000 neurons or whatever, to describe some phenomenon, local phenomena. It's sometimes extremely useful to be naive in the model, but it's a crime to be intellectually naive. You have to be aware of what you throw away and what is missing. And ultimately, the last point, 8, is important point. Writing down this type of dynamics as the standard model, it's the same as in physics. The standard model in physics is good for some things like particle physics, the spectra and properties of elementary particles. But if you want to explain the dynamics of a macroscopic object, it's completely useless. So even this level of abstractness that I write here, the standard model, even this level is going to be way too complicated to make sense unless we are simplifying further or building analytical tools, theoretical tools, simulation tools, statistical tools to probe this type of dynamics in ways that are more understandable or interpretable to us. So this is just the challenge of computational science. How far we can go, we'll see, but I think this is a very important goal. We have, I think, a reasonable minimalist dynamic framework. For most accounts, I believe this is good enough, but we have to still further develop intellectual approaches to start from this kind of microscopic, so to speak, dynamics and explain cognition. I'll end there.
Sorry, can I ask another question?
Yes.
Lecture about how we go from the microscopic deterministic to the macroscopic probabilistic models in physics. So I just want to like sum up the idea of the arguments or of the explanation, which we had in the I think the last slide of the first lesson. Is yes, exactly. So the idea that we get to the probabilistic is because we don't explicitly know the micro states and just assume a specific average, and therefore we derive, like, say, an average probabilistic equations from that. And if we would knew, like, still in the dynamics, if we would knew every single micro state, it would still have a completely deterministic system.
Yes, almost correct. I do not. I only object to the ignorance aspect that you mentioned. In other words, what I claim is the following: I have a system that, let's suppose, I fully knew it's all micro variables. I knew everything. Okay, now I'm faced with two options. One is I'm interested in the macro properties of that system. Okay, in that case, I can either use the good old deterministic dynamics to compute the macro properties, or I can make a fake distribution canonical ensemble as a mathematical tool to compute the macro properties of the fully elaborated microstate. Okay? It's just mathematics.
Yes, but this mathematical tools assumes that what I'm doing by doing this mathematical construct, I'm just assuming that this averaging works.
You can think hypothetically that there are ensemble of state. It doesn't matter. I don't think it's important. Whatever you assume, because it's not reality, you don't, in the words of Gibbs himself, he said, it's not an objective, canonical ensemble. There are many, many states, and you average, it's not an objective reality. It's an imagination. It's a mathematical artificial constant to get the same result that you would get if you would assume the system is fully deterministic and fully detailed microscopic. Number one. Number two, let's assume that I'm not interested in only macro properties. I'm interested also in semi-macro, in some things which are don't have this macroscopic. I'm interested in the properties of a certain molecule or groups of neurons or or groups of particles in my system, okay? Let's talk about that. In that case, if I know the full micro details of that system, of course, I will know the answer, right? Good. But the answer is not interesting. It's what I'm saying is the reason why I go to probability distribution is because the answer will not be interesting. Because tomorrow I look at the same group of molecules and they'll have different microstates. So it's not about not knowing the details of the microstate or ignorance. It's about what is interesting. In those cases, my interest is to know the distribution of micro properties across different initial conditions. Okay, think about this Brownian motion. You have, let's say, one particle and is making collisions with others. Okay, let's suppose I know everything. I know all the molecules that make collision with it. Okay, so I can take a photograph and say that this particle is here. But this is not an interesting statement because tomorrow I'll do the same experiment with slightly different initial condition and the particle will be completely different. So it's not about not knowing, it's about not being interested. The point is that in most cases, we are interested in properties which are stable under changes of initial condition or changes slightly the environment and so on and so forth, okay? The reason why we don't specify those degrees of freedom because we're not interested. It's not because we don't know what they are. Because it is a too transient and contingent answer, which is not of interest. What I'm really interested is what happened to this particle as times move on, or what happened to the particle as I initiate the system differently. That's what I'm interested in. I'm interested in statistics, okay? So my point is, what you said is right, but it's not a matter of ignorance because I cannot measure. It's because I'm not interested in this, in the detailed microscopy, because the answer will not be interesting. To just tell me that the particle is now here, and even if I can simulate, will tell me that given that the particle is here and I know everything, it will be there. I'm not interested. I'm interested in the rule, in the behavior. When I change, it will be the initial condition. Then the particle will be there and will move here. Okay.
Okay.
So
I have a second question about the very last part.
So this is what I mean by coarse graining. So we averaging even other initial conditions over other degrees of freedom. It just because the questions that we are interested are naturally in those cases will be statistical. The macro properties will not depend on the initial conditions on where all molecules are. This is why it's a different story. Macro properties will just be macro, and you can just compute it and get the answer. But when you look at the statistics of micro property or the behavior micro properties, it's not a matter of ignorance, it's a matter of interest. We are interested in the properties that are robust to changes in initial condition and so on.
Yes, but now let's go to the neural network, which exhibits a chaotic system, slide in the second second part of the lecture. So we can construct, put in the weights, and we have a chaotic behaving neural network.
Yeah, yeah.
Okay.
I'm with you. I'm listening.
So now the microstates, I mean, now say the microstates are very, very important if if let's say to determine basically to a certain degree the future. I mean, the idea of the chaotic system is that the microstates do count, and we have on a macro scale right now like different, let's say, behaviors.
This is true. What you are saying is absolutely right. This is a very crucial difference, thanks that you bring it up, between equilibrium in the thermodynamic sense, and non-equilibrium system. Absolutely right. In equilibrium system, this will not happen. Non-equilibrium system, you can have an organized dynamics on a macro scale, which will therefore affect the macroscopic properties of the system and the entire world in some sense. And if it's chaotic, it will be sensitive to initial condition. So I guess what you are saying here there is a mechanism for having a small change in the initial condition, in the microstate initial condition of the network, and potentially have a big change, macroscopic change.
So my final question is,
we'll come back to it. I'll come.
Okay,
back.
I'm just interested, like on the LSAT neuroscience level, like did we measure or did we measure any chaotic systems or proof for chaotic systems in the brain? Were there some studies which, I mean, on paper it works very nice. You can write down the equations for a chaotic neural network, but how do you prove, or how is the idea of like to say, well, our brain has chaotic neural networks, or what would be, or it's very likely that we have, because it's like if you put the weights in a certain, if you distribute the weights with certain properties, it's very likely to get chaotic neural networks. Or how would you approach this question? Or I don't know. Or are there papers claiming we have chaotic neural networks and giving some kind of proof for it?
It's a very good question. It's a very good question, not only for the brain. It's for dynamical systems in general. When chaos theory emerged, that beautiful theory about chaos in the deterministic system, and then people tried to apply it to experimental systems, fluid systems, collection of oscillators, all kinds of. And the question was, how do you know, if you look experimentally, how do you know that from experimental observation that the system, how you test whether it's chaotic or not? And it's a very hard problem, definitely in neural circuits in the brain. The most of the difficulty is that the notion of chaos is the notion of a specific feature of dynamics in an autonomous dynamical system. In dynamical system where there is no noise or there is no external input which oscillates and so on and so forth. Okay, you can have external input, but it has to be fixed in time. So this is what it's known an autonomous dynamical system, that the entire dynamics is generated within. This is the main problem, because there's almost never such a case, right? Because the brain is, you cannot take a neural network in the brain, circuit in the brain, and think about it as completely devoid of influences or even stochasticity. So I would say the best you can do is look at properties, dynamical properties of a circuit, and ask whether what is the best way to, best approximation. Is the concept of chaos useful, and what are the alternatives, right? So imagine you look at the EEG, very, very macroscopic measure of brain activity. And you see all kinds of oscillations, but you see that the spectrum is very broad. It's not nice oscillations. It's completely regular. Okay. So you can ask yourself, okay, so what's going on here? Is it a chaotic system, or is chaos a useful metaphor, or not only metaphor, useful model, dynamical model to explain such a complicated dynamic? So whenever you have complex dynamics, which complex, I mean, it has some kind of oscillatory behavior, but it's not repeated. This is the question. And the answer is, well, so I would say yes, but there is no proof. It's more like, is it?
You can always argue that there's a variable we didn't put in our system, which would explain all the noise.
Yes, but the point is the following. The difficulty is the following. It's easy to look at noise. By noise, I mean white noise, like thermal noise, and to recognize it from the kind of irregular dynamics that I'm talking about, like you see in EEG and other kind of rhythms, irregular rhythms in the brain. Okay, they don't look like kind of stochasticity like white noise. However, you can ask whether there are other sources of variability, which is like, you know, fluctuations in blood flow, or fluctuations in local temperature, or neuromodulations, which are not really part of the neural circuit. And they have dynamics, and so this is why, as you said, you're right, you can never rule out that there are these influences that give rise to them. So
is there some kind of theory that, like, if you put enough differential equations, enough variables together, you'll more probable get a chaotic behavior of the system, let's say? Or is it not the more likely, let's say, differential equations you put stack into a system, it's not dependent on what you by chance get a chaotic behavior?
I must say, if I go back to this type of equations that I showed here, okay, and fix Wij. So what, under broad assumptions, one can say that if Wij has a substantial random part to it, unstructured, random I mean unstructured, like you prune some of the connections in kind of random fashion, then it's generic, likely to generate a chaotic behavior. But when I say chaotic behavior, you have to be aware of the following things. Suppose I have this model, very not chaotic, converges to fixed point. What I'm saying, if you take this symmetric assumption and you add to it a small part which is asymmetric, okay? Random, you say Wij is Wji plus some random eta ij, not stochastic, random fixed, okay, in the architecture. Then what you will see that instead of going to the fixed point, it will go around and around in a chaotic fashion. So chaos is ubiquitous, but it may be in many cases a small effect. You can say, okay, so there's a little bit of noise. It basically went to this fixed point, but there's a little bit of noise. Okay, or chaos may be the whole spiel. So I believe that in kind of neural network dynamics that we are talking about, it's generic to have chaos, but it doesn't mean that chaos is a substantial player. It may be that it's just adding some little bit of noise into the system. In other words, it generates a little bit of noise. You understand what I'm saying? Again, think about this. Wij, take a Hopfield model, a symmetric W that stores some memories to the Hebrew or whatever. But now you say, okay, but you know, the brain is not precise. So now let me add a small random component to it. Random, not stochastic in dynamics, fixed. then this picture will be overall remain, but instead of going to fixed point, it will go to some chaotic fluctuations around this. And instead of going to this fixed point, it will have some chaotic fluctuations around this. I don't hear you. You have to unmute.
But still,
Oh,
this noise doesn't make it on a macroscopic. Like basically, I would say on the otherwise, the noise usually will kill the chaotic behavior on a microscopic scale.
Will kill the what?
The chaoticness of the system in a macroscopic scale. It's usually what noise does is usually it averages out, and we have only
No. You didn't.
around the 6 points. We'll have only.
I said noise generated by the chaotic behavior. I didn't mean external. I'm saying this will be a fluctuating, erratic behavior. Maybe I use noise. What I'm saying is that the system that otherwise will go to a fixed point will now wander around this fixed point because of the chaotic dynamic, not because of external noise. Whether this is, you can say fine. So there is some noise. It doesn't come from outside. It comes from inside. That's fine. But chaos is ubiquitous, but what is the role, how big an effect it is on the dynamics and on the computation, that depends on more specific assumptions about the circuit.